let us consider a cube C in the three-dimensional space, such that the side length n of C is an even positive integer. On each of the 6 faces of C, we consider an n by n grid of unit squares. A beam is a rectangular prism of size 1 by 1 by n. Observe that each beam has its long faces, which are drawn in red, and its square faces, which are drawn in blue. Returning to our previously mentioned cube, we consider beams inside it, which are parallel to the x, y, or z axis, and such that the square faces of the beams must coincide with some squares of the grids in the 2 opposite faces. This brings us to the main concept in this challenge. A cube C is said to be in equilibrium if the following 3 conditions are satisfied. First, C contains at least 1 beam. Secondly, no 2 beams have intersecting interiors. For the third condition, the interiors of each of the 4 long faces of each beam either touch a face of the cube C or the interior of a face of another beam. For the most simple example, the following cube of size length 2, which is illustrated in 2 different perspective angles and where the white point denotes the origin, is in equilibrium. Indeed, this cube contains the green, blue, and red beams. For each beam, 2 of its long faces touch the faces of our cube, while its other 2 faces touch the interior of the faces of the other beams. For another example, the following cube C, of size length 4, is in equilibrium. We can also make C in equilibrium by using a fewer amount of beams, as in the illustration. For the case of a cube in equilibrium, of size length 6, we have the following example. This brings us to the main question in this challenge. The main problem. Let n be an even positive integer, and let us consider a cube C of size length n. Find the minimum amount of beams which C needs to contain in order to be in equilibrium. Our method for finding the minimum is divided into 2 parts. First, we will show that, for an even, positive integer n, and a cube of size length n, we can use 1½ n beams to make our cube in equilibrium. At the second step, we will show that any cube in equilibrium of size length n must contain at least 1½ n beams. This will prove that the minimum amount of beams that a cube in equilibrium of size length n can contain is exactly 1½ n. Now, let us return to the first step in our method and construct a cube in equilibrium which contains exactly 1½ n beams. For this, let us first look at our cube from one of the sides of its faces. We start by inserting green beams alternately in the right upward diagonal of this face. Observe that at this stage the number of beams inside our cube is exactly n divided by 2. This follows easily from the fact that the side length of our cube is equal to n. Let us now rotate our cube in the right direction with respect to the current observed face. We insert blue beams alternately in the right shifted diagonal of this face, where again we choose the right upward diagonal. At this stage, we used N beams. Finally, for inserting the last beams, we choose a face, which is orthogonal to the previously two faces that we chose. For this, we rotate our cube downward from the face that we are currently looking at. We insert red beams alternately, in the right downward diagonal, of our currently observed face. At this stage, we used all of our 1.5 N beams. For example, when N is equal to 6, we have the following illustration. To prove that our cube is in equilibrium by the previous construction, observe that if we denote the green, blue, and red beams by GI, BI, and RI, where the index I is between 1 and N, then the long faces of the beam GI touch the faces of the beams RI and RI plus 1, and the faces of the beams BI and BI plus 1, for I between 1 and N minus 1. For the case where I is equal to N, the long faces of the beam GN touch the faces of Rn and Bn, and two faces of our cube. In the same way, we can show that each of the long faces of each of the beams, Ri and Bi, where I is between 1 and N, touch the faces of other beams, and faces of our cube. This proves that our constructed cube is in equilibrium. Let us now prove the other direction. We need to show that each cube of size length n, when n is an even, positive integer, which is also in equilibrium, has at least 1.5 N beams. For this, assume that we have a cube C in equilibrium. Let us denote by Bx, By, and Bz the number of beams, respectively, whose long edge is parallel to the x, y, or z axis. If at least one of these quantities is equal to 0, let us say Bz, then exactly n square beams are needed to make our cube in equilibrium. Indeed, if we orient our cube such that its bottom face touches the z-plane, then each of the layers of our cube, from bottom to top, must be completely filled. Hence, we assume from here and after that Bx, By, and Bz are greater than 0. At this stage, our approach is to show that the sum of the numbers of any two types of beams is greater or equal to n. If we add all these inequalities, and then divide by 2, we immediately obtain that we have at least 1.5 N beams, as needed. We will only need to show that Bx plus By is greater or equal to n, since the other inequalities will follow from the symmetry of our cube. Hence, to finish our proof, we will show now that Bx plus By is at least n, assuming that Bx, By, and Bz are greater than 0. For this, we again orient our cube so that its bottom face touches the z-plane. Let us consider the n layers of our cube, which are parallel to the z-axis, and have unit height. By our assumption, there exists at least one beam, whose long face is parallel to the x-axis, and thus this beam must be inside a layer L in our cube. Since our cube is in equilibrium, it follows that this beam must be touched from above by some other beam, if L is not the uppermost layer, and be touched from below, if L is not the bottom layer. Our main observation is that our beam cannot be touched from above or from below by a beam whose long face is parallel to the z-axis. Hence, two beams whose long face is parallel to the x or y-axis touch our current beam and are found in the layers which are above and below the layer L. Let us call these two beams by B and C, respectively. Then, we again observe that no beam whose long face is parallel to the z-axis can touch these beams from above or below. Hence, some two beams whose long faces are parallel to the x or y-axis touch the beams B and C from above and below, respectively. Continuing with this process, we conclude that each layer must contain at least one beam whose long face is parallel to the x or y-axis. Thus, the number of these beams is at least n. This equivalently means that Bx plus By is greater or equal to n. Thus, we proved the inequality that we needed, and hence our proof is finally complete.